Okay, so welcome back. Thanks for showing up after our third day of lecture. Let me just say the notes are available up front if you didn't get any. I actually noticed, a few mistakes as I was going through the notes, looking over them before the lecture. And I managed to update them. So if you wanted a sort of more accurate copy, you can look along as we go online. But it's not a big deal at the end of the day. It was just like sort of little small things. Okay, so what we're going to do today, we're going to break today into 3 lecture sessions. And they're all going to be about sparse recovery using L1 minimization. Okay, so we've talked a lot about sparse recovery in general. We looked at greedy algorithms, and we looked a little bit at L1 minimization on the first day. And then we talked a lot about L1 minimization kind of in the introduction to compressed sensing lecture at the end of during the second half on Tuesday. So what I want to do today is say, okay, look, let's actually really try to get a feel for kind of the mathematics of sparse recovery. And I think the best way to do that is we're really going to look, forwards to backwards about why L1 is good for recovering sparse signals. Now, granted, it's not the only way to recover sparse signals, but it's one which sort of sheds a lot of light on why it's possible. Okay, so really today is all about, we're given some observation y equals phi x naught, and then we solve min x L1. So remember, this is the sum of the magnitudes such that phi x equals y. Okay, so what do we want to know? The main question we want to answer is, when is x naught the solution to the above, the minimizer to the above? Okay, so that's what we want to know about. We're going to look at it actually in 2 different ways. We're going to look at this problem. So the first way is, in some sense, the sort of more general, not necessarily compressed sensing way, and that's, our first lecture is going to be about, it's going to be about a lot of things, but let's just say it's like necessary and sufficient conditions for this to be true. And this is going to use using duality theory. So using observation duality. And I'll go, some of you may or may not know what duality, like the dual of an optimization program is. I'll just talk about it a little bit. I'll try to give you enough information, to make what we say kind of relevant here. But needless to say, it's an important concept, and it really sort of sheds light on when this is possible and when it isn't. Okay, so then, what we're going to do in the second lecture is we're going to talk about basically if this matrix phi has the RIP, this implies L1 works. Okay, so in the first lecture we're going to sort of revisit our spikes and signs dictionary, and we proved these uncertainty principles on Tuesday, and we'll show how we can plug those into these necessary and sufficient conditions that we get from these duality conditions to show, when it's possible to recover this sparse decomposition using L1. But then, in the second thing, we're almost taking a completely different tack, and we're going to say, okay, let's suppose now that this matrix has this very much stronger condition, and that it embeds all these sort of pairs of sparse vectors, preserves distances between pairs of sparse vectors. We're going to show that, okay, not only does that mean that these sparse vectors are identifiable, but from sort of very, different, but still very geometrical ideas, this means that L1 will be good at recovering those vectors through phi. Okay, so that will be our second lecture today. We'll look at that in depth. And surprisingly, when you look at this stuff, we'll see it. I wouldn't call it complicated. There's, when we go through this proof, we'll be able to do it very comfortably, I think, in 40 or 45 minutes. And it doesn't require too much knowledge except maybe of the triangle inequality. It's basically like 13 different applications of the triangle inequality to get the result. Okay, so that's what we're doing. Then finally, what I want to talk about a little bit about at the end. We're not going to have a completely thorough discussion just because by this point you guys will have had enough. So 3, we're going to talk about stability. What happens, in particular, what happens if the vector that I'm looking at is not exactly sparse, right? But rather can be approximated by a sparse vector. There's another thing where it says maybe if I have some error in my measurements, does my reconstruction stay stable? That's treated in a lot of the same way that we'll talk about here. We probably just won't get to it today. Okay, so that's the agenda for today. Okay, so let's go to note 6. Okay, so let's start with something very easy. Again, what we're interested in is there the laser pointer? Okay. Oh, it's in. Oh, right. Okay. Thank you. Okay, good. Okay, so just as we've been talking about, what we're mainly interested is we're saying, okay, look, I observed some unknown vector x through, and we'll assume an underdetermined system of equations and see why. We'll make some assumptions about this underdetermined system, some very mild assumptions about this underdetermined system to start, and they're not that critical. It just it keeps us from having to put in caveats everywhere. So let's just start by saying, this underdetermined system, let's just say it has full row rank. So all its rows are linearly independent from one another. Okay, so what we'll be interested in ultimately is conditions under which, even though this is underdetermined, we'll be able to recover x from these observations. Why? Of course, sparsity is going to be what allows us to do that. But just to point out something which might be kind of an obvious point, but I think it's worth talking about. There are other assumptions that you can make. Forget about sparsity for a second. There are other assumptions you can make about x, such that you can exactly recover it from y. Right, so here's a simple one. Like, let's say, that we say instead of x being sparse, let's have a linear model for x. Right, so let's say that, our model for x is that it's in the range of it's in the row space of phi. So what does that mean? It says let's assume that the thing I don't know is a linear combination of the rows of phi. Okay, so that's that's a very linear model for what's going on. So we're saying it lives in this linear subspace. And it's actually pretty easy to see for this particular linear subspace, which has dimension m, if there are m rows, that I can exactly recover x by solving this program here. Right? And so what this program does is a least squares problem. It says of all the vectors x, such that phi x equals y, give me the one that uses minimum L2 norm. And so that's there's a well-known closed form solution to this program when phi has full row rank. I simply do it by applying the pseudo inverse of phi to y, right? And if I'm saying that y is phi times the measurements, I just replace y with phi x naught. And if my assumption is that x naught is in the range of phi transpose, right? So x naught is phi transpose alpha for some alpha, right? I can just replace x naught here with phi transpose alpha, right? And then what do I have? I have this times this, which is the identity, which just gives me phi transpose alpha, which just gives me x naught, right? So it's kind of easy. So it's like, one thing that and again, this is saying, this is going back to this case where, we were talking about, like, how should we measure a signal if we can do anything in the world? Well, if you know that it lives in a certain low-dimensional subspace, what you want to do is you want to arrange your measurement matrix as possible to measure everything in that subspace directly, right? And then, indeed, if you do that, just through the simplest linear algebra you can imagine, of course you can get an easy recovery of the signal back. Okay, and everything that comes with this will be stable as long as this is well conditioned, etc. Okay, so now again, what we're interested in is not this kind of linear model that X lives in this subspace, but in this nonlinear model that X naught is sparse. Right? So when I say X naught is sparse, what does that mean? It means there are only, say, S non-zero terms in X. For any particular locations for those non-zero terms. Of course, the model is that X lives in an S-dimensional subspace. But the idea is, since I don't know which of the locations that X will be non-zero to begin with, really what it is the union of these S subspaces. There's actually an incredible number of these S-dimensional subspaces, namely n choose S of them. Okay, so what we are going to focus on is say, okay, look, given Y, what we're going to do is we're going to estimate X by solving this optimization program, where this one is different than this guy, only because we're replacing the 2 norm with the 1 norm, right? So we minimize the sum of the absolute values in X subject to these linear constraints. We saw that we called this thing basis pursuit when we saw it in the context of choosing the sparsest decomposition. We also saw that this could be rewritten as a linear program. And we also saw, one nice thing is we also saw that, no matter what we say about phi or y or x, the solution to this will always have less than or equal to m non-zero terms, right? Where m is the number of rows in phi. Okay, but really what we're interested in is, if we really do believe that y is equal to phi x naught exactly. So this is our model. We don't have any noise involved for the lectures here today. What we'd like to ask is, first things let's do is let's talk about some necessary and sufficient conditions for X naught being, exactly the minimizer to this program. What is one set of things we can say? So in actually using, this idea of a dual of an optimization program, or the Lagrangian of an optimization program, we can actually come up with necessary and sufficient conditions without too much bother, right? It's actually not terribly complicated. Now, what we're going to do is after we come up with necessary and sufficient conditions, they're going to sit there and they're going to, what we'll do is we'll kind of take the sufficient condition and we'll turn it into something which is easier for us to deal with. Right? So we can get necessary and sufficient conditions. It's just it's not clear how to show that they're bad. So we'll actually refine the sufficient conditions in such a way that we can actually do a lot with them. And then we'll start to do a lot with them in a second. Okay. So here's essentially what we're going to do. So let me write down some of the key things here. So let's just keep these up here so we have them up here and we can point to them as we go. I'll try to write big. So we observe y equals phi x naught. We'll say that this guy, x naught, this is supported on gamma. So what I mean when I say supported, I mean that gamma is an index set, so it's some subset of 1 to n, and those are just the locations of the non-zero terms of x naught. So this gamma is what we'll call the support. Okay. So what do we kind of need for x naught to be a solution? Right. So tautologically, what are we saying here? So we're saying, okay, when is x naught the solution to this program? Well, it's the solution when for all other vectors x, such that phi x equals y, x naught has the smallest L1 norm of all of them. Right? Another way you can say that is if I take any vector h that's in the null space of phi and add it to x naught, that the L1 norm of that has to be greater than or equal to x, the L1 norm of x naught. Right? That's saying, essentially, if I'm sitting at this point x naught, and where I'll look at all the places I can move to stay feasible. So all the kind of directions I can move from x naught such that phi times wherever I move is still equal to y. That restricts me to moving in the null space of this matrix phi. Wherever direction I move, that means the L1 norm increases, right? It goes up or down. So kind of the picture you can have in your mind, right, is, or one useful picture to have in your mind, is if you just think of something like this. So here's like a sort of a baby picture in R2. So this is my sparse vector x naught. Oops, and this is so here's x naught right here. And this line here, this is the set of x such that phi x equals y. Right? And what does that mean? That means, if I move along this line, this would be something in the null space of phi. Right? So basically, so here's my sort of set of constraints. To move from x naught, if I add an h to x naught, and I want to stay in this feasible set, that h has to be in the null space of phi. So in a sense, when I draw a picture like this, that means that to stay feasible, all the x's, all the h's have to lie along this line. And what I want is whenever I add that, it at most keeps the L1 norm the same, right? So in this case, wherever I move on this line, it increases the L1 norm, right? Because if I move out here, I need to draw a bigger L1 ball for it to be included. Okay, so this would be a case where, for every h that's in the null space of A, right, this is clearly true. Okay, and then, if I were to draw a picture like this, right, this is clearly a case where it's not true. So if I move, this blue set represents my constraints, it means I can move in the null space and actually make the L1 norm much smaller. So that's the kind of the geometrical picture that we start working from. Okay, so that's just just sort of an easy definition. So we always have this kind of interplay between some kind of geometrical notion and or trying to see if I add something to x, if I can decrease the L1 norm, and this restriction that this vector I'm adding to x has to be in the null space of phi. It kind of will underlie almost everything that we do today, like these two things playing off against each other. Okay, so what is something good we can learn? We can actually very quickly get at, so we know that phi times h is equal to 0 just by construction. But we can actually get, a very nice kind of a geometrical property of h by doing a very simple manipulation. And actually, let me skip to the, let's just go through this. We can actually get kind of a very nice geometrical condition on h just by plugging in to what we want here. Okay, so let's try to see when this is true, right? So kind of what we want to do is develop a necessary and sufficient condition for this being true. Okay, so we can do this just by doing some simple manipulation. So let's just look at when this quantity is bigger than 0, and then let's just write this down, what this quantity is, right? So all we've done here is we've taken, this is the sum of the magnitudes of x naught plus h minus the sum of the magnitudes of x. X naught is non-zero only on gamma, right? So what does that mean? It means I can break this difference into two different sums. One is a sum over the support gamma, where both x naught and h are involved, right? So this is basically this thing on gamma. And then the other part of it is on the complement of gamma. So everything where x is exactly equal to 0. There, all we have is, the contribution of the sum of the magnitudes of h. And so all we've done here is just replace this by definition. Okay, so So then we know what we can do is we could actually say something very easy about this, right? So we can say, actually, this is, this sort of complicated thing here. We can just replace this by the sine of x naught times h, right? And that just comes from the fact that if I have two real numbers, a and b, and I look at the magnitude of their sum, right, that's greater than or equal to the magnitude of a plus the sine of a times b. And this is just it's a simple identity. So basically, how do you prove something like this? It's basically, you'd say something like a plus b is greater than sine of a times a plus b. All right, so that's one thing you can say for sure. So a plus b is greater than sine. So I mean, this is either positive a plus b or negative a plus b. So the absolute value, of course, was greater. And then the sine of a times a is just the absolute value of a, which is just the sine of a times b. All right, so it's just a simple identity, which sort of allows us to collect these three different terms into just one thing. Okay, so when we do that, we get a sufficient condition, right? What does it say? It says if we look at the sign sequence on the support gamma, right? So we look at the signs that x have, whether or not it's positive or negative, right? And we sort of take the inner product of that with the descent vector h, or take the inner product of that with h, right? And so what that means is it means that this is always, when I take the negative of that, that's always going to be less than or equal to the sum of the absolute values of h off the support. Right? And this is true for any h that's in the null space of phi. Okay. So that's good. That's necessary. That's sufficient. The condition, it also happens to be necessary. And that you say, okay, look, if h is in the null space, then epsilon h has to be in the null space, right? So that means that, of course, phi x naught plus epsilon h equals y, right? And then if I look at the L1 norm of that vector, I can again, break it up in the same way I did before. And then the idea is that, again, I can replace this by the sort of the sine of epsilon h with epsilon times the sine of gamma naught. But the idea is I can choose, this epsilon small enough so that the sign of this doesn't change. Right? So I can immediately show that this has to be strictly less than x naught L1. Right, so what that means is that this being true for all vectors h in the null space of phi, that's both a necessary and a sufficient condition. Okay. So that's interesting. So what does this kind of tell us? So again, it's what's on the right here is like sort of telling us, look, what do we need out of vectors that we remove to stay feasible? Like what kind of geometrical conditions do we need? And the geometrical condition we have, essentially what it's talking about is it says, look, it only depends on not necessarily the values that x naught takes. It really only depends on this set gamma, obviously, since gamma appears explicitly in both of these sums, and it also depends on the sign sequence of x naught on gamma. Right, so that's the first interesting thing, like whether or not I can recover x naught using this L1 program. It doesn't depend on the actual, and this is for exact recovery, it doesn't depend on the actual values that are in x naught. It depends only on the sign sequence of the active coefficient and the support set of the thing. So, when it comes down to what does that say, it says that, what does sort of the sign sequence and the support dictate? Well, it kind of dictates, like, where on the L1 ball do I live? Like, each of these points has a different support set and sign sequence, and each of the facets is the same thing. So it's really just a property of the facet on the L1 ball that I live on. So what it says is, if I live on, there's a better picture on the next page. So if I can recover, say, any vector perfectly on one of these facets of the L1 ball, then I can recover all of them perfectly. Right? So it's really not a property of X naught, such as like this sort of subset of things where the X naught lives on the L1 ball. Okay, so that's what we have. So we have a necessary and sufficient condition for being able to recover the vector X naught from these observations, y equals phi X naught. Right, and these 2 points are the points I just mentioned. It doesn't matter so much on X naught. Really what's important here is the set gamma on which X naught is supported and the signs of the elements on that set. Right? And so the magnitudes of the entries aren't involved at all. And again, this is something which is true when I'm making sort of very strict statements about perfect recovery of X naught. So if I want to talk about when I add noise and talk about stable recovery, we're not. It could depend on the sizes that are in X naught too. But at the end of the day, like perfect recovery from linear measurements using the L1 norm really only depends on which facet of the L1 ball you live on. Like, do I live here or at the point, and not on the actual like dynamic range of the values. Okay, so that's good. That's interesting because it's necessary and sufficient condition. The only problem is it's kind of hard to see where to go from here. Right? So now if I ask you, okay, I have even if I give you a signal and I give you a matrix and I say, can I recover this signal if I measure it through this matrix by using L1 optimization? You would have to test this for all H and null. It's not clear like what you would actually do. So what we can do is we can actually go further than this by sort of coming up with sufficient conditions. So basically refining this thing to the left. And so that's kind of what we're going to do next. But to do this, I think it's useful to take a little detour into kind of like a duality theory in optimization, right? And so that's it's a different way to look at like when we can perfectly recover this thing, right? So like one thing we said, and actually something that's going to get us a lot of more mileage later on, is that okay? Look, I can comfortably call X naught the solution to this optimization program if every time I add something in the null space of phi to X naught, it increases the L1 number. It's almost true by definition. So there's actually another very good way to talk about the when you're a minimizer of something, right? So like imagine you were just minimizing a function. Just imagine I'm just minimizing a function on the real line, like you're a senior in high school and you're solving a calculus problem. And you say, okay, when is this the minimizer? Right? So one thing what this first condition up here would kind of be analogous to be saying like, okay, if I move in any direction here, I make the function gets bigger. Okay, that's kind of definition of minimizer. We work from there. Now we're going to talk about is kind of a neat trick that you learn when you take calculus, and that's another way I can talk about the minimizer, especially when this thing is convex, is if the derivative is equal to 0. That's another way you can classify the minima of convex functions if they're smooth. And so that's essentially what we're going to do. We're going to say, okay, we're at a minimum of this L1 function when a derivative is equal to 0. Although we have to be a little bit careful because we have a constrained optimization program and we have something which we can't differentiate. So we sort of talking about derivatives and but it's sort of both things kind of fail, but they're actually both easily handled. And so here's what you do. You say, okay, here's just sort of a little tidbit from optimization. Okay, so let's forget about L1 for a second. Let's say I just have a general optimization program with linear constraints. Right? So I just ask you, I give you some function of x, and say find the vector x, which minimizes f of x, but subject to the constraints where phi x equals 1. So if two things. So if f is differentiable, and I didn't have those constraints, right? So just say I had unconstrained problem, you could do exactly the same thing as in this calculus case. So even if you have, f is a function now and many variables, but you can still take a derivative, where now the derivative is just a gradient and just find the value of x where that gradient is equal to 0, right? And that would be exactly the same as this derivative trick in calculus. Okay, but you can actually, when you're constrained, you can't quite do that, right? Because you have to also make sure that whatever x, because it might not be the case where, or almost surely will not be the case now that the gradient is going to be equal to 0, where the gradient is equal to 0 falls inside my feasibility set. Right? So not only do we have to minimize this, we have to minimize it subject to some constraints. Nothing says, and in general, it's not true that where this gradient of this function is equal to 0, that it has to lie in this constraint set. In fact, it's probably not. Right? In fact, if this is a norm, then even if it's say the L2 norm or anything norm that was differentiable, the only place the gradient is equal to 0 is at x equals 0. Right? So that's not really that interesting. Okay, so here's what you can say, and let's talk about why it's true. So what you can do is you could introduce the so-called Lagrangian, right? And so what you do is you just look at these constraints, and you just look at the difference between these two things, and you take the inner product with some vector v. Right? And then you can say, like, look, now I can make an optimality condition that depends on both x and v. And I'll just draw for a second why this is true. And what this optimality condition says, let's just say for a second that f is smooth, so I can take its derivative. And even though it's not the case for us with L1 norm, I'll talk about how to extend this. What a kind of a condition for being at the optimal point is if I look at the gradient of this function with respect to x, right, and then if I can see if I can make it equal to the gradient of this function, see if I can make it equal to 0 for any value of v, for these quote unquote what they're called Lagrange multipliers. So kind of here's what's going on when you do something like this. So if I think of, these contours as being level sets of my function x, right? So these are level sets of f of x. And then x is a vector here. Okay, and then I have some constraints. So different colors. So this is my constraint set. This is x such that phi x equals 1. Okay, so now what I want to do is I want to take the minimum along this line of this function. So the minimum of f of x is, say, here, right? That here, where the gradient equals 0, it's not along this red line. What the minimum is going to be here is probably going to be something like, right here or something. That's where the minimum is going to be. Okay, so what is this condition asking? So here's essentially what it says. So the gradient of f, right, at any point, so let's call this point x prime. So the gradient sort of looks like this. It goes orthogonal to one of these level lines. Right, maybe that's negative of the gradient. So the negative of the gradient goes orthogonal to one of these level lines. Okay, so what does this condition say? It says basically I can build up the gradient, right, out of a combination of the rows of phi. Right? So in some sense it means the gradient, or the negative gradient, is in the linear span of the rows of phi. And that has actually a very kind of obvious geometrical interpretation when you think about it. So basically what it says is, at this optimal point, what I need is the contour line, the gradient at the edge of the contour line, to be orthogonal to this red line. Right? So let's think about why I'm saying that for a second. So, when I say that the gradient has to be in the row space of phi, what does that mean? So the row space of a matrix, it's everything that's orthogonal to its null space. Right? And as I move along, vectors along, to move inside of this red line, but kind of as was argued before, so to move from here to here, I add vectors that are in the null space. So in some sense, the null space is what I'm moving along as I move along this red line. So what I need to do is I need to find something, the place that's orthogonal, to this red line, that's also sort of co-aligns with the gradient of one of these functions. Right, and that kind of makes sense, because if I ask you, oh, is this point the minima, right? Well, here's the gradient, right? And since the gradient isn't exactly orthogonal to the line, it kind of suggests if I move just a little further down here, I would get smaller, right? And so that's essentially what it means. So what you need, and likewise, if I was over here, I'd say, okay, if you move this way, it'd get just a little small. So what I need is the gradient does not sort of co-align with the row space of phi at all. And that's exactly what this says. So the null space of phi at all. So so with that, just another way of saying that is the gradient is in the row space of phi, or more to the point, there is a set of Lagrange multipliers v such that phi transpose v is equal to negative grad x f of x. Okay, so that's kind of this picture like this. There's a lot of deep theory behind optimization and duality. But really, this is kind of what you're after, right? You're after, okay, I can't just look for the derivatives equal to 0. But really what I want this kind of interface. In this case, we have linear constraints, so we can explain everything clearly. I want this interface between my linear constraint set and the gradient of f of x. We just need this geometrical condition, which actually makes a lot of sense once you start to write it down. Okay, so one problem. Right? This all relies on f of x being differentiable. And, the L1 norm, if you just look at something like this, you can immediately see, without having to write anything down, that this is, pointy, and there's no way that it's differentiable at all. Okay, so, and that's, and it's funny, because, we're sort of, just from an intuition standpoint, we're counting on it being having this singular structure for it to work. And that's exactly what is kind of going to make it work and recover these sparse signals. The fact that it's singular along these facets, right? So that it's not differentiable or not smooth is kind of like why it's good. Okay, but anyway, how does it work? Actually, you can modify this very easily. So there's a very nice modification of above, and what you can say is, instead of the gradient of f of x equaling phi transpose v or negative phi transpose v, what you can do is you can calculate what's called a subgradient of f at x. And this subgradient is actually a set of vectors, not just a single vector. It's a cone of vectors. And you could say, what is my condition is that, there needs to be a v such that phi transpose v is a subgradient of f. Okay, so what is a subgradient? It's actually easier to just, rather than define it formally, it's easier to just kind of talk about it in that one-dimensional case. So just forget about L1 for a second. Let's talk about the absolute value of x as f of x equals the absolute value of x. So this function looks like this. Okay, so talking about the derivative of f of x for x here is completely non-controversial except at one point, right? That right there. And so when you first take calculus, you say, okay, the derivative doesn't exist there. We're going to do something a little more sophisticated, and what we say is actually it's not that the derivative doesn't exist there; it's that there are kind of many derivatives, right? And so it's like, what's one nice property of the derivative of a function? So I have a function, and I look at its derivative here. The function is convex. What that means is if I draw a line, the slope of that derivative, the sort of whole function lies to one side of it. Not only that, this is the only line such that's true. Because if I perturb it a little bit this way, part of the function over here will lie past it. If I perturb it a little bit the other way, part of the function up here will lie past it. So what you call the sort of the gradient, the derivative defines as supporting hyperplane. Right. So here what we say is, okay, look, here the derivative is 1. Here the derivative is minus 1. Here we could have maybe lots of derivatives. In fact, we could call the derivative here anything between plus 1 and minus 1. Right? And so for that's exactly what the subgradient is. So the subgradient of f of t is the absolute value of t. It's just the sine of t for t not equal to 0 to 1. and it's any number you want between -1 and 1 at t equals 0. Okay, so that's how we kind of get around this notion of the L1 norm not being differentiable, is we say, okay, look, in some sense, there are places on the L1 norm, a lot of places, everywhere we're not on one of the faces of this L1 ball, where we have somehow many derivatives, and kind of all we need is this condition for one of them. That's kind of what we're saying here. Okay, so this idea, that we have the absolute value has many derivatives. We can translate that immediately to the L1 norm. So, just more generally, if instead of f of x is the absolute value of x, if now I talk about x being a vector, so now we can say f of x bar is the sum of the absolute values of the entries of x. Now, what are the, it's kind of easy to take the first constraint and put it down here. Now, what all the subgradient of f's look like? Well, they look like vectors u, such that u is equal to the sine of x naught. So that u is equal to the sine of x naught at entries where x naught is non-zero. So what does this mean? This means u of gamma equals plus or minus 1 at those points. And when where x is equal to 0, the entries of this u vector have magnitude less than 1. They can be anything there and still be in this, this quote-unquote subgradient set. Okay, so that's what it means. So basically, what are we looking for now? So let's just back up for a second. So we say, okay, look, we have this nice optimization condition. Right? And so, if everything's smooth and differentiable, we could say, okay, I can call x naught a solution to this program if I could find a vector, or if basically I find a vector v such that phi transpose v is equal to negative the gradient of f of x. If f is not differentiable, what I'm asking, okay, what I need is a vector v such that phi transpose v is in the subgradient of f of x. Namely, in this particular case of L1 minimization, I need a vector v such that phi transpose v is equal to the sine of x naught on the support and has magnitude less than or equal to 1 off the support of x naught. Okay, so this is a nice, let's just say, necessary condition which is almost sufficient for this this situation. So, given an n by n matrix phi and a vector x naught supported on a set gamma, if you're given y equals phi x naught, then x naught is a solution to 1. I'm not saying anything about being a unique solution. If I can find any v such that phi transpose v is equal to the sine of x naught on the support of x naught, and phi transpose v has magnitude less than 1 everywhere else. Right? And it's also true that if I can find a v such that off the support I'm strictly less than 1 everywhere, then the solution is unique. It has to be a unique solution. I didn't go into it here, but that's true. Okay, so this is another condition, and it's the same type of thing where, like, what am I asking for this to be true? Again, this doesn't depend on the values that are in x naught at all. It depends only on the support set gamma and the sign sequence of x naught on that support sequence, right? And of course, it depends on the matrix phi also, right? Because that phi appears explicitly here. Okay, that's good. So, what do we do? So this is good. It's somehow a little more manageable. I mean, my task now is all I need to do is search the row space of phi to look for something that's a subgradient at x naught, right? Where I have a very well-defined notion of what a subgradient means. That's what I have to do to see if this x naught, if I view it through phi, it's recoverable using L1 minimization. Okay, so that's one thing. So here's what a lot of the I'll go into a little bit, and we'll talk about in a second. So here's like what like many say of these papers in compressed sensing do, especially the early ones. well, actually, funny, very early ones and also very recent ones, because sometimes this is easier to do than the constructions we'll talk about later today. What they say is, okay, this is fine. It's still a little ambiguous because I'm saying, okay, how do I sort of search the whole row space? Well, one thing you can do is you can choose a particular dual vector and show that it obeys these conditions. Right, so this is called a construction of a so-called dual certificate at X naught. And here's how it works. Here's one thing you can do. There's many ways you could do this. But here's one way which kind of makes sense. We'll be able to prove kind of a very nice L1 recovery result next using something like this. And yeah, it's just a kind of a cute trick. Okay, so next. So here's one thing you can do. So you say, okay, let me write down this definition just because we'll use it again. So here's one way I can just construct. I can just look at one particular vector and say, is this vector in the subgrid? So here's what you do. So here's your matrix phi. So it's some m by n matrix. And then what you do is you have your set gamma. This is gamma. I pull these out to make the set phi gamma. But this is n by s. Okay. So the idea is, if x is the whole idea for this is, if x is 0 outside of gamma, then of course I can write, phi x naught is equal to phi gamma times x naught restricted to gamma. Right, so if I just take out all the non-zero terms and throw everything else, and then take out all the columns corresponding to the non-zero terms, of course these two things are going to be equal. Okay, so here's what you can do. You say, okay, let me take this matrix. This matrix is, in general, if I'm looking at a sparsity which is less than n, which is kind of the only thing that kind of makes sense to consider. The matrix will have more rows than it has columns. So, if it's full column rank, one thing I might consider is taking some u naught, which is basically I take the sign sequence of x, so z naught is the signs of x naught, and basically I apply the pseudo-inverse of this matrix psi gamma. I apply a pseudo-inverse to the sign sequence. Right, and then I say, okay, let me use that as my sort of Lagrange multipliers v. Right, and then the thing I'm looking at that I'm going to check to see if it's in the subgradient is phi transpose times those Lagrange multipliers. Okay, so now sufficient conditions. Now this, the point of doing this is we have two clear sufficient conditions. So one is, if this thing is, if this is indeed invertible, right? So if phi gamma t phi gamma, if that really is full column rank, which has to be checked because nothing says that it has to be true. Then immediately what you have is on the support, u naught is equal to the sign of x naught. That's by construction. Because that's like basically saying, on the support, I just put another gamma here, and then phi gamma transpose phi gamma times its inverse. It just gives me z naught back. Okay, so if it's invertible, you know that this sort of expression is well defined, and you have this condition that that u naught of gamma is equal to the sign of x gamma. Okay, then what you have to do is you check that if, one is holds, so this expression makes sense, I just have to check that everywhere off the support here, that u naught is less than 1. Right? So that's one thing you can do to get a sufficient condition for L1 recovery. You simply say, okay, let me look at this submatrix, phi gamma. So here I'm saying, I give you a matrix phi, and I give you a S-sparse vector x naught that's supported on gamma and has sign sequence z naught. And I say, can I recover x naught if I observe it through phi? And you can say, if I construct this, if phi gamma is full column rank, and when I construct this vector, it's less than 1 everywhere off the support, then the answer is yes. So it's a sufficient condition for being able to recover these things. Okay, so let me just say also, like with complex vectors, since we sort of have Fourier transforms floating around, you can do almost the same thing. All we mean by the sign of you just have to kind of change what we mean by sign. So the sign is, it's not +1 or -1. It's basically, if I write it, a complex number in kind of magnitude phase form. It's the phase of this is wrong. This should be e to the j theta, not theta here. So it's it's the e to the j theta part. And also, you're not really, when you're doing L1, everything we say, it's again will be true, but you just have to, whenever you see a sum of magnitudes, remember the magnitude is going to be the sum of the imaginary square root of the imaginary part squared plus the real part squared. Okay, so the point is everything extends to complex valued vectors with almost no differences. Right, so you actually get these exactly this set of same conditions. Instead of transpose, you write Hermitian, and that's it. It's the sign sequence is going to be a general point on the unit circle rather than +1 or -1. That's all that changes when you go to complex in the context of this theory. Okay, so that's good. I'll tell you what, it's 2:54 now. Why don't we break for 7 or 8 minutes? So we come back at 3:02, and let's just talk about application of this. Okay, so let's break for 8 minutes.